Assalamu alaikum. Welcome to the second lecture on power electronics. In today's lecture, we shall discuss the first kind of a semiconductor device that we will study, and that is a diode. So let us start with the current lecture. Diode is a two-terminal device that is the most simplest device used in power electronics. It is an uncontrolled device, that is, we cannot control once a diode is turned on or when it is turned off. There is no external signal which is applied. It is actually a two-terminal device which is shown by this symbol. We already have much information about how a diode works that we have studied in our earlier course on electronics. So one of the terminal is known as the anode and the other one is known as the cathode. The applied voltage VAK should be greater than some threshold, which is usually 0.7 volt for a silicon diode. For a gallium arsenide diode, this VAK should be greater than 1.1 volt, and for germanium diode, the threshold voltage should be greater than 0.3 volt to conduct a current through a diode. In power electronics, we are mostly interested in knowing the capability of a diode in terms of the switching characteristics. So if I draw the IV characteristics of a diode, let us say this is the voltage and this is the current. So I come up with two different modes of operation for this diode. The first thing is that we have applied the positive potential to the anode and the cathode is connected to the negative terminal. Under these circumstances, the diode becomes forward biased, and considering it an ideal diode, there shall be no drop across this diode. It will act as a short circuit path, and therefore the current flows in the positive direction from anode to the cathode. So this is the direction of the current IF. This means that in an on state, the diode conducts the forward current. However, it has no control on blocking the voltage, and therefore this is the point, or this is the axis where the diode actually operates when it is in an on condition. If I reverse the polarity of this diode circuit such that I connect the negative terminal with the anode of a diode and the positive terminal with the cathode of this diode, then the diode do not conduct because it's a reverse bias device now. Under such circumstances, it is said that in an off state, the diode blocks the negative voltage, right? So it blocks the negative voltage, and consequently no current flows through diode when it is in a reverse bias condition, and therefore this is the axis at which the diode operates. So in a nutshell, if we see here, diode is actually capable of allowing the current in forward direction current and reverse voltage blocking capability. This showcases that a diode is actually a signal quadrant device. So we can also say that a diode is actually a single quadrant device, because on the IV characteristics, it is only capable of allowing the current to flow in one direction, and it is only capable of blocking the voltage in one direction, and that is when the voltage is applied negative with respect to the anode to the cathode. These are the diode characteristics when it is used as a switch. Now if you see here, the diode characteristics can be attributed in terms of two different types. The first one is a static characteristics, and the second one is known as a dynamic characteristics. Static characteristics refer to the VI graph when the diode is forward biased and when it is reverse biased. Notice here that unlike these small signal diodes that we have studied in our earlier course on electronics, this forward current versus this voltage in a forward conduction mode is not as exponential as we have seen for a small signal diode. So maybe if I draw for a small signal diode, the current may go like this. However, here we have, because of the properties and because of the material that we have added to enable a diode to operate under high voltage and current stress, this rising slope for the forward current is not as exponential as we have seen for the small signal diode. This one, on the other side, a diode is capable of blocking the voltage up till some particular limit, and so is the current, and therefore these 2 points are based on the data sheet values of a given diode. So any diode that we use has its own limitations in terms of the maximum allowable current and the maximum blocking voltage, and therefore the datasheet value defines what is the maximum current a diode is able to conduct and what is the maximum voltage it is able to block. This whole region on this side with the positive voltage here is known as the conduction region, and this side with the negative voltage side we call it the blocking region. When a diode is reverse biased, it operates in this blocking region. Notice here that despite it is able to block the negative voltage, there is still some current which is known as the reverse saturation current that flows through a diode even if a diode is connected in this particular configuration, and that is known as the reverse saturation current. Now for power electronic devices, we are more interested in knowing the dynamic characteristics, that is the behavior of a diode when it is suddenly connected to a source or when it is suddenly disconnected from some source. That is, we try to have a transition between the on state and the off state. So for instance, let us say that we have, this is the time and this is the current IF, which is the forward current, or IAK, the anode to cathode current, and the diode is currently on. Now this fall of the current depends on a lot of factors, and that is very important in power electronics because most of the time there are inductances which are connected in a given circuit that defines the rate of change of the current from this forward direction to this 0 point. So the reverse recovery or the dynamic characteristics of the diode establishes that this current will not come to 0 instantly. Rather, the diode goes into a state where it conducts the current in opposite direction, and that is because of the charges which are enclosed in the PN junction. So notice here that when we have a PN junction available here, for instance we have P and we have N, and they are forward biased, that means that this junction is very thin now and the current is flowing from anode side to the cathode side. Then we do have the minority carriers which are present in both of these two segments. In the P side we have the minority carriers, in the N side we have the minority carriers, and those minority carriers require some finite time to recombine with the majority carriers and get neutralized. During this process, because the power electronic devices are designed to conduct a large amount of current, therefore a finite time is required for them to recombine and to get neutralized, and during that time the diode remains short circuit despite the fact that the voltage has been reversed, and that particular time is known as the reverse recovery time of a given diode and is attributed in terms of TRR, or the reverse recovery time of a diode. Notice here that this reverse recovery time is dependent greatly on the rate of change of the current, which is DIF over dt. These are usually attributed in the data sheets, and some data sheet it is something around 100 ampere per microsecond something. So it's a quite a fast process in some of the diodes that are designed to operate at higher switching frequencies. And this DIF over dt is because the most of the diode circuits contains the inductances that define the rate of change of the forward current, and therefore it is attributed in terms of dIF over dt. This reverse recovery time is an important parameter in defining the maximum switching frequency of a diode. So you may see that a diode which is capable of, which is actually a line frequency diode, it fails under the switch mode power supply operation, where the switching frequency is as high, maybe at 25 kilohertz or 30 kilohertz. It is because that diode do not have enough time to recombine the charges before the new cycle appears, and therefore there are special kind of diodes which are designed to operate at high frequencies, and still they are able to conduct large amount of currents. So this TRR is an important factor in deciding the maximum switching frequency of a given diode. It has two segments. The first thing is known as the TA. Let us say this is the TA time. This TA time is a time during which the conduction, because of the minority carrier presence in these segments, the process actually starts. The reverse recovery actually happens, and that happens till the peak of the current IRR, which is the peak current during the time of the reverse recovery. After that, this TB time is actually a damage control time, and this defines that now the process of neutralization of the charges is initiated, and therefore the current starts decreasing until a point where the reverse current becomes equal to 0.25 of the reverse recovery current IRR. So this is, and this happens till we reach 0.25 of the peak current of the reverse recovery. After that, this current which is shown here, this is attributed as the reverse saturation current I0 of this given diode, because the reverse recovery current is there once a diode is turned off. So till the time we reach the peak value during a reverse recovery process, to the time where the current becomes equal to 0.25 of the peak current, we consider that the diode is now turned off, and whatever current is flowing through that diode is attributed as the reverse saturation current. Now this rate of change of the current dIF over dt times this TA defines the peak value of this current IRR. So IRR is the peak current, and that is given as TA into dIF over dt. Also, if you notice here that this creates sort of a triangle here, and therefore using the concept of the area under a given curve or the area under this triangle, we can establish what is the total charge which is enclosed in a diode during the process of this reverse recovery, and therefore we can say that this QRR is equal to the peak current IRR into TRR divided by 2, which is nothing but base into height divided by 2, which gives us the area of a given triangle. So for high frequency switching circuits, TRR of a diode defines the upper frequency of the operation. Also, the most important point here is that this current IRR, it has to flow from the cathode to the anode, and therefore this current flows to the source or the other elements that may have the current carrying capacity different than that of this diode. This implies that such devices may have to carry this reverse recovery current as well, in addition to whatever current they are following, they are capable of handling, and therefore the determination of this IRR is a very important factor in choosing the devices that are used in a circuit, in a switching power circuit. Let us see a given data sheet of a particular diode that is quite useful in designing a switch mode power supply. The data sheet provides us very important information about a device. It contains the typical characteristics of a device. It also provides us the maximum allowable limits that can be imposed on that given device. Also, Also, it provides us the mechanical characteristics that are quite useful in designing the printed circuit boards. So let us see what is in the data sheet of this diode, which is RURG3020C. This particular diode is an ultra fast diode as claimed by this Fairchild semiconductor company, which is quite a famous company in this particular area. It is able to conduct a forward current of 30 ampere and 200 volt is the maximum voltage that can be applied. This means that if we connect the diode in some given circuit, the maximum current, forward current that can be supplied through this diode without damaging it, it is equal to 30 ampere. Also, if we connect negative terminal here such that we want to block this voltage, then the maximum blocking voltage is limited by this 200 volt. Other than that, we have in these features, we can see that this is an ultra fast recovery diode with a TRR in just 50 nanosecond. If you notice here the shape of this diode, this comes in a 247 package that contains two diodes rather than one diode in each leg. So it has the two diodes which are separate. They are combined with one cathode, which is the central limb. So the overall structure here is that we have this kind of a structure here. So we have this anode 1, this is anode 2, and this is the cathode. So the total current that can be conducted through this device is equal to 60 ampere, because this 30 ampere is for each leg of this particular diode. How we come to know that? If you see here, there are absolute maximum ratings which are given in this data sheet, and that says that it is for per leg, which means that each of this anode, this is leg 1 and this one is leg 2. So the combined capacity of the current that can be flown through this diode is equal to 60 ampere. Other than that, we have the repetitive reverse voltage that is equal to 200 volt. It is an important factor. For instance, we have connected a diode in a circuit which is a rectification circuit. Under that circumstances, when the diode is reverse bias, it has to block a certain voltage. That is because it is a repetitive process. Therefore, the peak repetitive reverse voltage is attributed by this 200 volt. We have a DC blocking voltage that is equal to 200 volt. Also, the average rectified forward current per leg is equal to 30 ampere, and that is at a temperature of 145 degrees centigrade. Other than that, we have a repetitive peak surge current as well as the non-repetitive peak surge current. Surge currents are an important phenomena in all those circuits where we have the capacitive filters, right? So we will see in our later classes that whenever a diode is connected in a rectified circuit with C filter, we have large amount of peaky currents that flows through the diodes because of depending on the charge available on this capacitor, and that is quite an important parameter in selecting a given diode, and that is given by the non-repetitive peak surge current capability that is equal to 325 ampere. Another important point here is that the maximum power dissipation is limited to 125 watt, and thereafter we have this avalanche energy concept and the operating and the storing temperature, which are -65 to 175 degrees centigrade, right? Next come is the electrical specifications, which defines the electrical characteristics of this particular diode. So we can deduce several important points by this particular information. For example, it says that Vf, which is the drop across a diode when it is conducting, it is typically 1 volt when we have a temperature equal to 25 degrees centigrade. at 150 degrees centigrade with the same amount of current flowing through the diode, the maximum drop is 0.85 volt. Using this particular information, one can find out what are the conduction losses or the on-state losses of this diode. So for instance, for this VF of 1 volt and with a forward current of 30 ampere, the on-state losses is equal to 30 watt. This parameter, which states the reverse current when the diode is in a blocking mode, provides us information about the blocking losses or the off-state losses of this diode. So for 200 volt, we have 250 microampere current that flows in this particular direction. If this is 200 volt and this is 250 microampere current, then the total blocking losses for this diode is merely equal to 50 milliwatt, which means that this diode is an accident diode when it comes to the on-state losses and the off-state losses. Also, we can see here that this reverse recovery time is quite a small time. Therefore, this diode is capable of operating at high frequencies. Notice here that this dIF over dt is set at 100 ampere per microsecond, and it is mainly because in power electronic circuits mostly contains the inductances, and therefore this parameter is an important parameter that defines at what rate of change the forward current shall actually drop to the minimum value, and therefore this makes quite an important parameter in defining what is the peak reverse recovery current of a diode. Also, if you notice here, we have an important parameter R theta JC, which is the thermal resistance junction to the case, and that is equal to 1.2 degrees centigrade per watt. This means that for each watt of power dissipated, the temperature, that is the junction temperature, rises to 1.2 degrees centigrade, right? So notice here in this particular table, it is given that 125 watt is the maximum power dissipation which is allowable for this diode. So 125 watt multiplied by 1.2 centigrade per watt is the total junction temperature that rises when the diode is operating at its maximum power rating, right? That is equal to 150 degrees centigrade. Notice one very important point here is that this is the degree centigrade per watt rise. It is in addition to the already stated parameters which is given here as Tc is equal to 25 degrees centigrade. So if I add this with that 25 degrees centigrade, then at a power dissipation of 125 watt, the device shall be operating at 175 degrees Celsius, which is again attributed here as the maximum operating temperature of this device. So under this particular condition, when the device is only consuming 30 watt or it is only dissipating 30 watt, the device temperature is barely at 30 into 1.2 degrees centigrade plus 25, that is equal to 25 plus 36, and that is equal to 61 degrees centigrade, which is quite low compared to the maximum value which is given in the datasheet. Coming forward, you can see here that some typical performance curves are given. The first one is the forward current versus the forward voltage. If you notice here, there are three different curves here that corresponds to three different values of the operating temperature. The first one is the 25 degrees centigrade, which is the standard testing condition. Then they have tested it at 100 degrees centigrade, and the last one is the maximum allowable temperature condition, that is equal to 175 degrees centigrade, right? Now if you notice here that as the temperature is increasing, the forward voltage drop Vf is decreasing, right? So at 25 degrees centigrade, the forward voltage drop is something around 0.7 volt. However, at 175 degrees centigrade, the forward voltage drop is merely about 0.4 volt. This means that this diode or any other diode is actually a negative temperature coefficient device. Negative temperature coefficient device. And this is a very, very important parameter while we connect two devices with negative temperature coefficient in parallel. So that creates a challenging environment for us. What else we can get through this figure number 1? So now if you see here, suppose that you want to find out what is the turn on resistance R on offered by this diode. That can also be estimated using these three curves. So for example, I want to see what is the turn on resistance for this 25 degrees centigrade curve. So for that, R is equal to V over I, but rather than taking a point value here, I shall be taking a range of the values delta Vf over delta If to get an idea about the average, or the to get an idea about the average on resistance during the operation of at 25 degrees centigrade. So for example, I may say that I can take these two values here, right? So this is delta V and this is delta I, and thereafter I can see what is the on resistance of this particular diode. The next graph is the reverse current versus the reverse voltage graph. Again, they are designed at three different values: 25 degrees centigrade, 100 degrees centigrade, and at 175 degrees centigrade. We can actually determine what is the off-state resistance R off using this particular graph, and that is again by combining two different points and by taking VR divided by the delta IR. So these two graphs provide us the on-state resistance and the off-state resistance of a given diode. Next, we have some important characteristics available here as well. Again, these are the reverse recovery characteristics for this particular diode, and these are the test circuits that validate that this actually happens if the circuit is applied this particular pulse, and this is the diode which is under test, or the device under test. And here we have sensed the current which is drawn here. So again, it explicitly defines the region of the TA and TB. Notice here that the ratio of TA and TB defines the softness factor of a given diode. So you can see here that we may have a diode with a very fast recovery. This one is actually a soft recovery diode. We may have some diodes. There are some diodes available that have abrupt recovery, reverse recovery process. However, despite the fact that the reverse recovery process is actually a problem in power electronics, we do not go for a fast recovery diode, because they creates other problem in the circuits which are well beyond the scope of this particular course. And last one is the mechanical characteristics of this particular diode, and they're all be used for using the PCB software. However, you can see here that the TO247 actually defines the package, and which gives you the desired pads with the appropriate distance between the two pads and the three holes automatically if you select for TO247 package. Coming back to the diode, let us see what are the issues when we conduct a diode operation such that we have two diodes connected in parallel. So as we have seen here that a diode is actually has negative temperature coefficient, right? This means that we need to be very careful while we can connect two diodes in series or two diodes in parallel, because a slight difference in the characteristics of a diode owing to the manufacturing irregularities or the manufacturing non-idealness, it may lead to the failure of the other diode. So let us consider two diodes which are connected in series. So let us say we have these two diodes. They are connected in series, supposed to block this particular total voltage which is supplied. So let us say this is VD1 and this is VD2. Now if you notice here that because these two diodes are supposed to block whatever is the voltage applied here, this V, they have to block this voltage V, and we have connected them together because in our laboratory we do not have the exact blocking rating of the diodes available to tackle for this input voltage. So therefore we have used two diodes in a series configuration to block the voltage by sharing the voltage among each other, right? However, if you notice here that there might be some discrepancies or irregularities or non-idealities in the manufacturing process, such that or the reverse or the blocking region of these two devices differs by, for instance, by this particular point. Notice here that this diagram is not up to scale. Now suppose that if this is the total applied voltage here, if this is the blocking voltage that is to be blocked, this means that there will be the reverse saturation current for each of the diode. Let us say this is ID1 and this one is ID2, right? But because this circuit is connected in series, therefore there shall be only one reverse recovery current which shall flow from this point to this point. And therefore, to satisfy that particular thing, if I say that this is the actual reverse recovery current which is allowable because they are series circuits, so they do not have they cannot have two different values of the reverse saturation current. Therefore, each of the diodes shall be operating at different operating voltages VD1 and VD2. That is actually a problem. So there are two different voltage that are blocked by these two diodes, and there might be a discrepancy that may lead to the failure of one diode. So how can we tackle this particular issue? To tackle this particular issue, let us connect a resistance here and one resistance here. Let us say this is R1 and this is R2, this is D1 and this is D2. Now what we can see here is that suppose this is the total current which is supplied. Let us say this is IS. That is equal to ID2, okay, IS. Let us say the current that flows through this diode D2 is IS2, and the current which is flowing through this diode is IS1, or the saturation current of the first diode and the saturation current of the second diode. So IS is equal to IS2 plus IR2. This is IR2. Because we have now an alternate path for the current to flow, so both of these two diodes can operate at different reverse saturation currents while having the same voltage blocked by each of these two diodes. This is equal to IS1 plus IR1, because at this particular node here, then whatever is the saturation current, it goes through this diode and the rest of the current shall be routed through this resistance R1. IR1 is equal to VD1 over R1 and IR2 is equal to VD2 over R2. If R1 is equal to R2 is equal to R, then the diodes shall have different voltage across them. However, if we vary these resistance, let us say we have the one of these two or both of these two are actually adjustable, then by adjusting the value of this R1 and R2, we can force these two diodes to share equal voltage across themselves. Let us see how we can do that. Suppose that as an example, let us say that this is the voltage, this is equal to 5 kilovolt. It is to be blocked by these two diodes. We further assume that the diode D1 and D2 have different operating characteristics because it is practically impossible to generate two devices with exactly replica characteristics. There is always some deviation in the characteristics. Let us say that the diode D1 has a characteristics where the IS1 or the reverse saturation current flowing here through this diode is equal to 30 milliampere, and the reverse saturation current flowing through this diode D2, that is the IS2, that is equal to 35 milliampere. We also say that this R1 is equal to R2 is equal to 100 kilo ohm. Together this network is supposed to block this 5 kilovolt. So what happened here is that using this particular expression, this minus VD, which is this voltage, is equal to minus VD1 minus VD2. This implies that VD2 is equal to VD minus VD1. So using the equation that we have derived earlier, IS1 plus VD1 over R1 is equal to IS2 plus VD2 over R2. Now because this R1 and R2 are fixed, this IS1 and this IS2 is given, I can actually find out the value of this VD1. By substituting this value here, I can find out what is the value of the VD1, and that turns out to be equal to 5 kilovolt divided by 2 plus 100k over 2 into 35 into 10 to the power minus 3 minus 30 into 10 to the power minus 3, that are the two reverse saturation current, and this comes out to be equal to 2750 volt. And using this thing, VD2 is equal to 5000 minus 2750, and that gives you 2250 volt. Notice here that the only difference between these two diodes was the reverse saturation current with 5 milliampere change only. The voltage sharing capability has greatly reduced to 2250 for this VD2, and most of the voltage was blocked by the diode VD1. Now suppose that it was given that these diodes are capable of blocking 2600 volt, then this diode would have eventually led to the failure. This means that once this diode would have been failed, the diode D2 would also have been failed. So therefore, the choice of the resistance plays an important role in defining the exact amount of the voltage sharing between these two diodes. So how can we solve this thing? Let us say we want to have equal voltage shared between these diode D1 and D2. For that, for equal voltage sharing, R1 and R2 are to be adjusted. accordingly. So how can we adjust these two? Using this particular expression, using this expression, we can say that IS2 plus VD2 over R2, that is equal to IS1 plus VD1 over R1. We want to have VD2 equal to VD1 equal to 2500 volt. We can specify that let the resistance R1 equals to 100 kilo ohm. 100 kilo ohm, sorry, right? With this 100 kilo ohm, if I substitute the values in here with all this IS1 and IS2, this R2 comes out to be equal to 125 kilo ohm. And that actually creates the voltage VD1 equals to 2500 volt and VD2 equals to 2500 volt. So equal voltage sharing can happen if we have a resistance connected across the particular diode. And this is very important in those circuits where the voltage blocking capability of a device is enhanced by connecting several diodes in series. Now comes the concept of the parallel connection. Now in parallel connection, the problem comes, in manifold. For instance, let us say we have this particular circuit, right? Let us say we have the circuit. This is a very simple circuit. Now, as you have seen in the data sheet, that the diode has a, let me first of all write it here, parallel connection here. As we have seen that the diode has a negative temperature coefficient, which means that if the current that flows through this particular diode D1, if ID1 is greater than this ID2, then the temperature across the diode D1 will be higher than the diode, higher than the temperature of the device D2. If this is D1 and this is D2, TD1 means that the voltage of the D1 will decrease. That will result in an increase in the current ID1, and consequently this snowball effect leads to the failure of this diode D1. Therefore, there requires a current sharing mechanism for parallel connected diodes. And what is that? Let us see. For that, we connect a network like this, and this is R2, this is L2, this is R2, this is R1, and this is L1, and we have these two coupled inductors available here. Now suppose that if D1 or the ID1, which is the current flowing through this diode D1, try to increase, or it increases, then the voltage across the inductor VL1, that is equal to LD over dt, it also increases, right? This creates a corresponding voltage. This creates a corresponding voltage which is opposite in polarity across this inductance L2. Consequently, L2 drives the diode D2 into more forward biased region, and hence ID2 increases. Consequently, ID1 decreases, and this process moves on and on such that we have more or less the same amount of current shared between these two branches containing the diode D1 and the diode D2. So let us summarize the diode. For the summary of the diode, let us write summary of the diode. It is actually a two-terminal device. It allows the forward current and it blocks the negative voltage, right? So over the VI characteristic curve, this is the region of the diode. This region is the only playground of this diode. We do not have any control on a diode. There is no external signal that is supplied to a diode. So the operation of a diode is automatic. So therefore it is an uncontrolled device, and the circuit state defines when it is turned on and when it gets turned off. The reverse recovery time TRR defines the maximum operating frequency of a diode, right? And lastly, that current sharing mechanism and the voltage balancing circuit is required when connected in back-to-back series, when connected in series or in parallel respectively. So in the next class we will discuss the silicon control rectifiers, which are kind of a control device that allows us an external control that can be imposed on it. Although it is a multi-coordinate device, so we will explore how this device has a switching characteristics that are suitable in power electronic circuits. Thank you very much. Allah Hafiz.